anyways, closing the parenthesis. So it's my pleasure to present today's talk from structural equation modeling to latent causal representation learning for more trustable machine learning. Long title.
Yeah, thank you, Christian. So thank you for being here and sharing your time with me. I'm happy to talk about this topic. I will have two parts. The first one is about one previous work I did about structural equation models. And by the way, I want in the future to work more on causality and mainly latent causal representation learning. That's why I will, at the end, in the second part, take time to give some motivations about it and to try to convince you that it could be an interesting research area, maybe to catch more a trustable ML. Okay. So first about me, I'm undergraduate from the University of Montpellier. It's south of France. I did after that also my PhD in the same place at Institut Montpellierin Alexander Grothendieck. So it's a mathematical lab with fundamentals and also applicative areas. And next, I had a nice opportunity in the laboratory, in the League Lab. It's the computer science lab at Grenoble University, in which I worked on machine learning area, mainly on ensemble methods, in which I developed some smooth decision trees and consistency decision trees. And after that, I obtained a nice position at CentraleSupélec, and now I'm an associate professor, maître de conférence, we say in France, at CentraleSupélec, mixed lab. We have also two research domains that are mathematics and also computer science. And here you have some sample of research interests I have today, mainly on machine learning area. And I hope in the future to work more on causality field, and I hope also I could convince you about that. So, as I told you, first I will start by a structural equation model and an approach based on an algorithm I developed in the past. I will first present the context, the approach, and show you some interesting applications on real data. I will start by an example just to give you some vocabulary and basics. So here we will assume this is based on a real data set I will present after. So here we have different observed variables in gray. This is what you have here and here. We have access to location variables such as altitude, longitude, some rainfall variables. Also to indexes about enhanced vegetation and some counts regarding the abundance of 27 species of trees. And what we will do with this kind of model is to look at a kind of structure in the data set, and we can organize these different observed variables by different blocks. We have here a block in which we are trying to catch information associated to the vegetal activity. Here, some variables associated to local environmental conditions. And on the top, we can talk about tree population. And what we assume that could correspond to the expert knowledge is that these blocks of variables here on that we have about local environment conditions and vegetal activity will explain finally and have an impact on the tree population. We decide to talk about observed variables for characteristics that we have on the data set, and we will call this kind of yellow variable latent variables, because inside we have latent we don't have access to values for these concepts, and we will try to catch some values for them via the approach I will present. And at the end, the edges will map the relationship between the variables, between observed variables and latent ones, and also between latent variables only. We could have many blocks, but in the next presentation, I will, for simplicity reasons, I will focus only on 3 blocks, 2 explanatory ones and 1 which is dependent. So about the formalization, before to present mathematical formulas, I will just introduce the fact that we will have in the formulas 2 kinds of formulas. One will be associated to the latent variables only. This is what we have here in orange. And the others will associated to the gray regions, in which we will have observed variables that will be wrote as as latent variables and some weights. I will present it, and noise. So first, about the latent equation, we call it the structural equation in the model. We assume that we can write it like this. So we will have here a dependent factor G, which could be written as F1 with a weight C1 plus F2 with a weight C2, that will map the impact of the relationship, the weight of the relationship between these 2 elements, and a noise here that we have. So I said factors because in some literature we can call it factors, but this is latent variables. And now when I join the other part of the model, we will have new equations that will appear. And what I want to show you also is that we can also deal with extra covariates and add some here in each block T1, T2, and T extra covariates that will allow us to add inferences, to add other determinants than factors, than latent factors, and will allow to discriminate between inference we could have in the factor and from extra covariates. An example could be for the geological substrate. It's very naive, intuitive, because depending on the geological substrate, you can have some different tree abundance. So this is the idea. So now we have the full model with the structural part and measurement part associated to the observed variables that we have here. And you can observe that we will have also a summation notation with the latent variable G here, with the weight, it will be here a vector B plus a noise. And here we will deal with extra covariate, and in the first column with a kind of mean tendency in the model. And this is the structural equation model. In the literature, no, first I will talk about assumptions I did, and after I will talk about literature. So we assume here that we have I instances from 1 to n that are independent. For the latent explanatory factors, we assume that there are Gaussian distributed with a 0 mean and a variance covariance equal to the identity. The same for the noise that we have here. And we assumed also that they are all of these 3 concepts are mutually independent. For the measurement model, we also have a Gaussian distribution assumption for the noise with a 0 mean, and for the variance covariance, we assume that we have a diagonal matrix with a sigma parameter that we have to estimate. Of course, we can do more complex model with more parameters, but this is what I did for starting. And here I use the notation theta for the set of parameters that we have to catch to be able to fit the model. So we have matrices for DD1, D2, vectors for B, A1, A2, and after real scalars, C1, C2, and sigma parameters. And the goal will be to catch values for the parameters, but also to reconstruct the latent variables. We haven't only the parameters to catch. We also have to be able to attribute values for latent variables. And to do that, you have two kinds of families in the literature. The first one is called factorial methods. That's why sometimes I'm using the word factor for latent variables, in which the first work, the main work, is proposed by Jaurès-Cogg, and he's mainly working on the analysis of the covariance structures to do that. He has also some distribution assumptions, Gaussian distribution assumptions. And after, we have a family that is called PLS, that is mainly based on component assumption. By components, I mean, you can have PCA in your mind. Basically, you consider each latent variable as a linear combination of observed variables in the block. You have here some characteristics just to distinguish between them, but I think, the main about assumptions, the differences between what we consider is a latent variables. And regarding the estimation, here we will more focus on the structure of variance covariance matrix and likelihood maximization, but here we will more work on least squares technique and regressions. And I think this is the main, and I can come back on it if you are more curious about the differences. So now what I proposed is an approach based on EM. As you know, EM algorithm is working with latent data. So it's the first idea you can have in mind. And it will help us to estimate simultaneously the parameters theta and also give values to the latent factors. And to do that, we use likelihood maximization. And the positive part is that thanks to this approach, we will work on all the model and not negligate a part of the model, because as you remember, ASC approach from Jaurès-Cogg use also likelihood maximization, but to estimate the model, the approach only focused on measurement models, the gray parts we had in the diagram, and not the orange part. So thanks to that, we can use all the model, which is more informative. Just a few words about EM algorithm if you don't know it. So we have here theta for parameters, C for observed data, and H for missing data. And P theta will correspond to the probability density of the join here of Z and H data. And the idea of this algorithm is that there is an equivalence between the fact to maximize the likelihood on Z and the fact to use the conditional expectation on the joint likelihood here we have. So Z with the missing data. And to maximize the criterion, what the algorithm is doing is to working on two steps. The first one is E for expectation, because the algorithm will compute the conditional expectation we have to deal with here. And after, he will, in the next step, the M step, he will maximize this conditional expectation to be able to catch the value for theta in the next iteration. If you take time to write it by your hand, you can explicitly obtain a formula for the likelihood maximization in our situation with the structural equation models. this is basically what we have here. And you can see inside that we have the factors, the latent variables here in orange, and also the squared of a part of them. So to maximize it, we need to have values for these latent variables. And to do that, and also values for parameters to do it iteratively. And to do that, we have to solve this equation. If you are more curious about it, I can give more elements after, but you have to solve it to obtain values for estimate the parameters. And when you do that, you can see that you will obtain explicit formulas. And that's nice. You have here 2 examples, but there is still a last step to do, is to catch values for these latent elements. F and G are the tilde will correspond to the fact that the notation means that estimation, because I wanted to distinguish between the parameters and the latent variables. But this is the same idea. The bar corresponds to the average, empirical average, and phi 1 and phi 2 will correspond to the squared of factors f1 and f2. And to be able to give them values, what we propose here is to explicit the Gaussian distribution of the latent data given the observed ones. So, and when you do that, you use some basics in statistics that will allow you to obtain the formula for this distribution. And after, the idea here is just to look at an estimation for the factor G, such as the first element of the mean vector of this Gaussian distribution here, conditional Gaussian distribution. And you can do the same for the next factors. And for gamma, phi1 and phi2, it's easy. You have basically to use the formula of the variance, because when you do that, you will obtain this expectation of the squared minus this mean squared here, and you can extract an estimation and then a value to attribute to these squared latent variables, just by using this Gaussian distribution explicitly. And after, it's easy. You can work with the formulas, the mathematical formulas that you have. You only have to push inside the values iteration after iteration for parameters and for latent variables. You have here a picture of these different formulas for this situation with 3 blocks. Yeah. You have here a graph that explains the process. So first you have to deal with an initialization. So to do that, you can use PCA and obtain some vectors for the components and use it as first values for the latent factors. And thanks to the formulas, obtain values for the parameters. And step by step, you will do the E step, then the M step to iterate and obtain values for the next iteration. And you do that until to satisfy the stopping criterion that is just here. You can use this, but you have many formulas for stopping criterion that you can consider. And you only have to give value for epsilon here. That could be this one. You have to take it as small as you want, dependent on how much you want to stabilize the values. And in this situation, on 100 simulated data, what I obtained is that we have a convergence with only 5 iterations, so it's very quick. And we obtain good values for factors. Here we can compute the correlation between what you simulated and the values you catched. And you have a value close to 1. And for parameters, you can compute the distance between what you catch and what you had, and you have something that is very close to 0. I won't talk a lot about numerical results because it could take a longer time. And basically, just I tested different configurations of the size in the dataset to have an idea about what kind of dataset we can deal, and we have results. So this is the dataset associated to the application, to the first example I presented to you. So now I will switch to the real applications. This dataset is about a tropical forest of the Congo Basin, in which you have 1,000 plots that correspond to plot cells, in which you can count for each species the number of trees, and you have access to different variables: rainfall, enhanced vegetation index I presented to you previously, and an extra variable about geology, in which you have 5 levels of substrate. So to use the approach is very easy. First, you can look at the PCA, take the values for the vectors corresponding to the components for the initialization, and work like this. So this is the model, you remember. We have here the explicit formula we used, because as you can see, we can consider an extra covariate only for one block. This is what we have here. And after, for the next formulas, you can only deal with vector with one values to have this average parameter, to keep this average parameter in the formulas. And you can compute the parameters, give values, obtain reconstructed factors and values for these latent variables. You can do many things with these results for interpretation, analysis, and for example, a kind of thing you can do is look at C1 and C2 values you catch, and you can finally say that for the first block of variables, we will have with them more impact on the abundance of tree species than with the other block of observed variables. Now I will switch to another real application I did on health-related quality of life. It was about women that had breast cancer. So now I'm trying to step by step do a matching with some areas that could interesting the members of the lab. I did a collaboration with clinicians from Institut du Cancer de Montpellier. And the clinician's goal was to evaluate the clinical benefit of a new anti-cancer treatment. And to do that, you have 4 criteria to satisfy. You only have to satisfy one to show that the treatment is interesting to sell it in the market. And one of them is the health-related quality of life criteria. It's difficult to measure it explicitly because you have different dimensions associated to the quality of life. This is also subjective. It's depending about my opinion, your opinion, and also during time, it could be very dynamic because now I could have some different sensitivity than in 1 month. So to have the data, they use questionnaires and they give it to the patients at different visit time. You have to fill it and they will work on it to extract the data. You have here the classical questionnaire that they use for all cancers. This is the basic, the main, in which you can observe that we have different dimensions. One block of dimensions is about physical aspects, emotional aspects, etc. And another family of dimensions will be about if you are tired, if you have nausea, pain, many kind of symptoms. And you have a particular one here, which is a global dimension that basically they ask to the patient globally, how do you feel? You have 2 questions because for one item is associated to 1 question. So after they have access to the results of each questionnaire, they will compute some scores in the way to have to obtain a high score when you have a high level of quality of life for the functional dimensions, what we had in this part of the slide previously. And for symptomatic dimensions, we have high score when we have low level quality of life. The idea is to have two different directions for these two different families. And after that, when you obtain these scores and you compute it such as you have values between 0 and 100, a kind of percentage, you can apply the model and work on it. So what the clinicians did previously to work with them is that to make some longitudinal analysis dimension by dimensions. We had 15 dimensions, and they studied for each dimension, for example, the diarrhea or another dimension, how the quality of life for this dimension will evaluated during time and during the delay in which they will take the treatment. And thanks to this EM approach, what we propose to them is to deal with latent factors and finally to work with less dimensions and do this longitudinal analysis more quickly. So first, we used additional questionnaire because for the data set we had a data set about women with breast cancer. We have specific questionnaire that we can merge with the previous one, in which it will allow us to have more dimensions, for example, associated to the sexuality or the symptoms on the arm that you can have when you have operations, chirurgy. So this is what we did. And you can, via the structure of the questionnaires, use it as a prior knowledge about the structure of the mathematical model and write it like this with two factors, two latent variables, two blocks of observed variables, and one particular variable here about global health staging. This is what we did. And for the longitudinal analysis, you only have to fit the model for each visit and catch for each visit the values for the set of parameters and for latent factors. And after that, in a second step, you only have to deal, for example, with a linear mixed model with these different factors that you reconstructed and the explained variable you are interested in, so the global stature of quality of life. You can also add some extra covariate. I won't give a lot of details here about this application, but you can deal with situations in which we want to test two ways to take the treatment. For example, here we tested when the patient take in the first period only radiotherapy and after a new molecule, letrozole here, and an other group of patients in which we can test the fact to have it simultaneously. Sorry, first simultaneously and after one step and a second step. To do that, you only have to play with an extra covariate, in which you have one for one group and 0 value for the other group, and obtain interesting results and be able to compare the differences, if you have differences between reconstructed factors you have at the end. And if you have differences, you can say something. Maybe there is a difference about the way you take treatment. And if there is not, you can say, okay, no difference, do what you want. So this is the idea. And for the last step about the longitudinal study, you only have to keep inside all the elements you have, latent factors, and the variable you want to explain and extra covariates, and do with a big criterion, try to catch the best model of that. Here you have just the way we deal with linear mixed models, in which we have a fixed part, a random part. The random part is mainly associated to the subject-specific random effects to give you informations on instances by instances, and in in contrast to this first part that will give you information about the tenants. Okay, this is just a way to modelize these different concepts and to have information about these different aspects in the model. With big criterion, what we obtained is that the best model is this one, in which we have the latent factors. So it means that the latent factors are very interesting to have it in the model and give interesting information. We have also a part here about individual part of the patients that could also explain the variable we are interested on. And what I want to say here before to switch to the causality field is that if you look at the correlation between these two factors, when we did that, we obtained a huge value of correlation. So this is interesting because I told you in the beginning that about the assumptions that we are considering the fact that the factors, explanatory factors are independent. So here we can ask some questions about this strong assumption. So maybe we have to relax a part of this assumption. So I will switch this. And now I will talk about limitations that we have. So the first one is what I said just now about the independency, but we can also want to push more deeply these different relaxations we can do. For example, we can think about the fact to relax the distribution assumption. It would be nice to don't have only to deal with Gaussian distributions. It could be also interesting to extend the approach to a more general structural models and not only these situations I showed you, give more freedom to the model to identify the structure. So this is also associated to this point. And we can also want to upgrade the wall of the different edges, because I told you we are considering the fact that if we have a huge value for C1, it means that the first explanatory of block of variables is has more impact on the variable that we have to explain. But this is purely statistical. Okay, we are in the first level of the causation. So inside we can have some spurious correlation and not all the causation aspects. I will say a few words on that after. And it could be nice to take advantage of the causality field to allow to these edges to have their real role on causation. And we can also explore more deeply the time dimensionality, the analysis with time, thanks to the field of causality, and consider nonlinear relationships, because as you see in the formulas we had at each time observed variables times the weight plus a noise. So we can try to think to more generical way to write it mathematically. So regarding the first limitations, I told you causal discovery could help because we have inside many tools now that are available to work on that and to infer the causal structures or a model underlying the observed data we have. So it could be interesting to take advantages from that. We have many subfields inside. We have some methods that are constraint based, in which we are just working with conditional dependency tests to recover these causal structures. And the well-known is PC algorithm, but there are many and many now today algorithms that we can use to do that. There are also score-based methods that are maybe more close than what I presented, because you have only to work with score functions. It could be a big criterion or Bayesian Dirichlet to guide the search of the good graph causal candidate for your data set. And we can find some score functions in which we have a likelihood inside. So this is an interesting way of work. And there are many others, also ones that are working with non-linear relationships. Here for the ages, we can also take advantage of causal graph discovery with latent variables that could help us to catch some latent causal representation. And this is very interesting for the machine learning area and deep learning area, in which now we have many approaches that are proposed in the literature to catch some characteristics. And we have some papers. The last one I read is one named Flint. You can take a look about this paper, and they catch some particular characteristics for the representation. And if they do some tests, they observe that all of these characteristics are disentangled with particular information about the pictures. So maybe it could be very interesting to work with that and try to build on this kind of characteristic, a kind of latent causal representation. Try to catch the causal graph we have with them and try to understand more deeply what the deep learning model is doing. So it could be very interesting to work on that. And yes, regarding the time dimensionality, we can also think about the idea to deal with latent causal graph as an invariant causal graph during time, and think about some additional graphs we can merge on it at different time and obtain a kind of shifts for each of this time and work with that. There are many possibilities for the nonlinear representations. We have also yet some tools with ANM, in which we have here a function to parents mean the variables that we have at the beginning of the age, and after here we have the child of the parents. So this is the causality notations, but this is the same that what I presented with Y and X and the age between them. And you have also recently different also models with function of function, in which you can have also inside the noise and deal with more complex representation and models. So to take a step back before to conclude, I want to talk more generally about AI and ML field, in which recently we observed that AI wave faces to big issues about prediction, decision, and efficiency. We observed, for example, for predictions that we can have issues with, for example, out of distributions problem. I have here an example with cows in pictures, in which we can see, you have here the reference. We can see that when a cow is in a classical context, we have no difficulty to predict a cow, but when we have more different original context, such as a beach, we can have difficulties to predict that this is a cow. So this is basically the situation in which we have, we are talking about a confounder in causality, in which here the confounder will be associated to the context in the picture that will disturb the correlation and disturb the model prediction. So just before that, yes, we are expecting AI approaches with that are more fair, more transparent, more accountable, and I mean decision more explained and model more explained, more robust, etc. And causality field could be a good tool to do that. Just to do a match with classical problems associated to the confounder, you have here an illustration from Bradiniel course that you can have on YouTube. It's very pedagogical, and you have an example about that is very illustrative about sleeping person that sleep with their shoes on, And if you look at the headache after when they are waking, you can say if you haven't access to the information that the night before they drink a lot of alcohol, you can't know that maybe the headache could be associated to the night before. And we can do the causal association with the fact that maybe if you sleep with your shoes on, you will have a headache. And there is no sense. So this is the idea that we have with causality, in which we are trying to discriminate between confounding association and causal association to avoid these spurious correlations with confounders. I won't talk about many technical details associated to the causality, but I think that I can't say nothing about two notions that are intervention and direct cause. Interventions is the fact that you have to force a variable to take a particular value. For example, for shoes on variable, we can say that we will enforce the fact that the people will sleep with their shoes, and we will enforce people to sleep without their shoes to study the phenomenon. And when you do that, you will block here these edges. And because you are blocking it, you will avoid this confounding association and finally work only in a causation situation, which is more rigorous. This is the idea that you have underlying this difference of probability in which you have to be careful about the fact that there is a difference between intervening and conditioning, thanks to this do operator. So this is the idea, the basic idea. There are many other tools, technical tools that you can use. The best one is about ATE. This is the average treatment effects that you can study when you are dealing with clinical trials in which you have treatment. In our previous illustration with shoes on, shoes off, the shoes on and shoes off could be the treatment. It's the position of the treatment. And yes, there are also similar way of ML with observational causal discovery, in which you can work with data, infer causal models, and also work with functional causal models and many other approaches that I cited previously. Here, just if you are curious, I propose to you a list of papers or books associated to different topics, ML, computer vision, or latent causal representation that are very interesting. And to survey, it's a sample of papers. If you are interested about it and you want to just learn a little bit and have your own opinion about the interests of considering causality or no. And now you have in mind a sample of questions that I have in my mind and I want to work on in the future, and I hope start new collaborations. So if you can think that it could be some overlapping with your interest, research interest, don't hesitate to tell me, or we can take time to try to build it. And we can collaborate with many formats. I'm trying to prepare an INRJC for the next year. So this is the more quick deadline, but there are many options with different research projects that could be maybe, I don't know, if that could be between Canada and France, or workshops, summer schools, tutorials, internships, co-supervision. So that's all. Thank you for your attention. And here you have some references I used for this presentation. If you have questions.
Any questions? I will look at the chat. Any questions in the...
Yeah, I have a question. Like for the EM algorithm that you used, so you have to like come up with this EM like algorithm for every, like, I don't know, you call it a data set, I guess. For every situation that you study, you have to derive the whole thing again. Like it's, but because from what I understood, like the graph that you create is, I mean, you have to do it by hand. Like you decided that there were groups of observed variables, and like it doesn't seem very general, like as an approach.
Yeah, this is one of the limitations that I'm talking about at the end, and that's why also I think that the causality field could help, because you have some algorithms that allow you to catch this structure, and with the freedom of this algorithm, you can catch different structure, and it could be very interesting to compare them and discuss with the expert about his own structure, the prior knowledge he gave to you. So, because in these situations, for example, with questionnaires, we take into account the fact that there is a prior knowledge on the construction of these questionnaires via psychologists' work or clinicians' work, etc. So we use it and take into account about it on the formulas. But of course, you can assume that you haven't access to this knowledge, or you can assume that maybe it could have some differences or some new aspects you want to take into account that this expert don't know.
Yeah,
So,
also there could be some bias in that knowledge. Like when you talked about the quality of life for the patients, it seems that the categories were, I mean, I couldn't read everything, but like some of them make sense, but others are like debatable, to say the least. Yeah. So really better to just discover these groups, like instead of fixing them beforehand, because that looks like a bias to me, at least in the model.
Yeah, you're right. Yeah.
Any other questions, either in the room or in the chat?
I know it's a little bit different about what you do day by day, but if you have questions after, don't hesitate to send me an email. Okay.
Well, I have a question. So my question is about explainability and interpretability. So let's say you discover these causal factors and you go to the clinicians and you present, okay, well, we found, let's say, 4 major factors. They seem to be, structured in such a way. How do you actually explain what these factors represent and mean, and how, like, to communicate? Because, like, this is a little bit unsupervised in a way, right? So how do you?
Yeah, it's depending about the application. If you are dealing with pictures, you can, for example, observe that some latent factor will correspond to some characteristics in your picture. For example, I don't know, ear of an animal or this kind of things, and you can discuss with this information. Now, clinicians, it's a particular aspect, because many times they think that they know better than you what they are doing. They have their own expertise, so it's difficult to say them, okay, maybe you have to exploit this and this because I observed it with my mathematical tools. So it could be not easy to discuss with them, but you can confront the different results, and sometimes it could give to them new intuitions, or you can also discover things that they don't know. I don't know, maybe some combinations of molecules that they could try for treatment if you are dealing with the geometrical aspects of the molecules. So I think many degree of freedom that we can exploit.
Right, because I saw that in your diagrams you had names for these factors, but in general, this is sort of like a high-level assumption that you make that they represent this kind of information, right?
Yeah, here the words I used, it's because you can also look at the PCA that will comfort you on the organization of blocks that you are doing. And when you do PCA, you do that. You are looking at the block of variables around one direction and trying to interpret what is the concept and under that you have to consider. So this is the same principle I used, but maybe you can construct the name of the concept by discussion with the experts.
Right. Marco?
Hi, very nice talk, by the way. It's very interesting, thanks. And I have a question about, so from what I understood, in most of the cases when you want to use causality, you need this intervention, right?
Yeah, this is one way, one
Okay.
subfield of causality.
But in this case, would you actually like get your data set? Because how you intervene in a data set that is predefined?
Yeah, so in your data set, you have different variables. And what you do with the algorithms is that you are looking at some, it's computationally speaking, you will look at some, what is the word? Interventions you will do, one variable by one variable. So you have many combinations. That's why PC algorithm that I told previously now has many critics because it's very costly. You have to do a lot of tests when you are fixing one variable and looking at the difference between the intervening distributions, if I can say it like that, and do different tests. Now, I don't have all the literature in mind, but now I know that there are algorithms that are more flexible, more quick, more smart, that we can use. So the idea is to explore more about it. And you have also what I told about the score functions that could guide your search process, in which you will have a kind of likelihood maximization with penalization that you can use also to give you more intuition about what kind of graph you can consider or not consider. Kind of situations. Yeah.
Okay.
Mm-hmm.
Thanks.
There's a question from Ahmad. Could you please explain a bit if you see the factors in function with time in longitudinal data? So, right, so.
I'm not sure to where the question.
I guess he's asking what kind of factors you can find in longitudinal, like temporal factors. What kind of factors do they represent? Ahmad, correct me if I'm wrong. Or maybe if you found some temporal factors. Yes.
Maybe it wasn't enough clear because I talked about many things very quickly, but the idea was to catch factors for each visit, so at different moment, different time. And when you do that, you will have values for this factor and these factors at different time. So in your linear mixed model, you only have to push them. So you have the time information inside. And after, you will do a kind of model selection to observe if it's interesting to keep the factors inside the modelization or not.
Right.
Idea.
Maybe if I can extend the question, have you looked at sort of the trajectory of these factors over time, and whether the trajectory is sort of connected to some, disease or disorder?
Yeah, I don't remember exactly, but yes, we looked at the kind of curves we can obtain with the tendency, with the first part, and also the specific tendencies for each patient. And we observed interesting things. This is what I will remember. It was maybe 6 years ago. So. But you can look at on the paper in appendix. We have many graphs.
More questions? So I have one more question. Seems like there's no more question on the chat. It's kind of like a very open question. You talked about Judea Pearl, and I think I remember he was the one that made this talk about the deep learning alchemy. criticizing deep learning, that we're finding correlation, not causality. And it seemed at the time, I think it was like 2019, or maybe you remember. Anyways, that scandal, it made a big stir, and people like were pushing, yeah, we need to move away from deep learning and sort of like go back to causal models. And there's sort of like a movement in that direction, but I'm not quite sure it generated the traction that we expected. So I just want to know like your opinion on that, whether we're going in that direction, whether we can expect a big change in deep learning soon. Or...
My opinion is that we can catch the best from different fields and try to build on interesting things. So I don't think it's a good idea to opposite people and different cultures. What I really think that we can take advantages of causality in deep learning models to trying to catch this kind of black box way, but we have many works to do before, I think, because what we can see in literature is that many papers are working for this causal graph discovery, are working on simulated data. And when you want to work on real data, at this time, it's still, there are some difficulties. It's not so easy because we have in deep learning many variables and it could be costly. So we have to find a way to deal with all these different difficulties. And it's not easy, but by the way, that's why we are doing research. We want to try to take on this kind of situation. This is what is interesting in our work, I think.
Right. Well, I think it's another question from Ahmad. You mentioned explainable term in your future plan. People usually use deep learning for that, while your model looks like explainable. So could you please clarify the term explainability here? Ahmad, I don't think we understand your question.
I will try to answer.
You can actually, Ahmad, maybe you can speak, right? We can hear you. And try speaking.
And your mic is on, or your speaker is on.
Oh yeah. I think it's on. This one is on. That's why I muted mine.
Okay. Maybe I can try to say some words, and if I'm far away, you can just.
Okay. Hello. Hello. Are you hearing me?
Yeah, we hear you, Ahmad.
Hello, Myriam. Thanks so much for your great presentation. In fact, just a quick comment about your talk. I saw that you used in last slides, you explained that you used the term of explainable, and your model looks like not related directly to deep learning. So what is the action of explainability here, if you want to use this term?
Yeah, if we want to do a kind of overlap with deep learning area, because causality fields is not only associated to machine learning area, you can use it for classical statistical approaches, as I presented before. This is the first step and the easy step. But regarding the deep learning area, what you can do is that work with the example I told about it previously. For example, you have some approaches now, such as Flint. You can look at on the Google Scholar about this paper. You have some representation, some deep learning approaches in which you are dealing with particular characteristics. You are trying to isolate some characteristics that are very informative and have a kind of good Shapley value, for example, this kind of works. And when you do that, finally, you will have few variables. It could be 20, 30, and an interesting number of characteristics with what you can deal, and try to catch this kind of causal graph that will give you more information about a kind of latent data process generation. And this graph, if you look at it such as a data generation process about your latent characteristics, you can talk about a kind of explainability. If you are able to associate these latent characteristics with concepts, and we can do that with picture data. When you have in one characteristic something, you observe that this is associated to ears, and on other part is associated to, I don't know, luminosity. I'm saying, and thanks to that, you can have a kind of explainability. Of course, you can consider different levels of explainability, but this is the basic idea.
Thank you so much. And have a nice day.
Thank you.
Thanks, Ahmad. All right, so I think we don't have more time for questions, so let's thank Myriam one more time.
Thank you.
If you have any wish to ask her questions or ideas for collaboration, just feel free to.
I'm in Jose office, so don't hesitate to come short.
Awesome, thanks. And I think we're not going to have any more seminars until probably September. I could be wrong, but at least a lot of people will be on vacation, so we'll let you know. And please, if you don't receive the emails for the mailing list, please write to Marie or myself or Eric.